So the next talk of this afternoon, in celebration of Lorenzo's anniversary, will be by Enrique Pujals. And coincidentally or not, all of the titles of these talks are very interesting, attractive. BBB, Blenders, Beyond and Before. Please, Enrique, it's a pleasure to listen to you.
Okay. Well, the pleasure is mine. So yesterday I was showing to Emilia this, the drawing that I did. And she say, do you know what does it mean BBB in TikTok? He said, no, I don't know. This mean, what did you say? Bored beyond belief. You say, well, it's boring beyond belief. So I hope that it's not going to be so bored, this one. And if this, I'm sorry. So anyhow, so it is what it is. So what is the idea? So basically I'm going to focus on Blender. And of course, we will have to talk a little bit about how Blender started and what was the original meaning. But also I would like to talk a little bit about how this concept have evolved and have arrived to certain maturity. Let me see if I can change pages. Okay. And sometimes we want to talk about the maturity of a tool or a mathematical object. And the idea of this maturity is related to the fact that the object is going beyond how this mathematical tool or this object or this concept was designed initially. So we know that for many centuries, a line was just a straight line, and we know that a line is more than a straight. And we can vision different geometry, and this is coming from the fact that we are not thinking about a line in terms of how we draw it in elementary school, and we can envision another geometry. And so this is coming from the idea that certain concepts are conceptualized and going beyond about what was imagined in the beginning. And also the maturity is sometimes related when what involves the tool is when the tool can be applied beyond how it was envisioned at the beginning. No? But it's true that we also can fall in love with all the tools that we develop, hoping that this tool could become universal. The classical example is the lever. No? We have this famous sentence by Archimedes, who say that give me a lever long enough, a fulcrum on which to place it, and I shall move the world. No? So this idea that sometimes they envision this tool and they believe that this tool could be so powerful, and the reality is dry. And so the tool this is just the reality of a lever, you know, something pretty lonely. Anyhow, so the idea was to talk about before Blender and beyond, and so the talk was going to be divided in 3 parts. The first part is about before. We're trying to say a few words about the notion of robust chaos, or you want to say robust mixing or robust transitivity, and how was addressed classically this problem about robust chaos. And from there, let's try to see we can extract a principle. And let's see how the Blender appears in this picture. And the idea is that the way to find this kind of robust chaos and then is trying and going beyond that is keeping this principle and beyond the classical paradigm that was brought by hyperbolicity. And the beyond is what I will try to explain later at the end, and maybe it's going to be short, is trying to abstract the property of the Blender and see if we can move away from Blender while remaining a Blender. What does it mean in this? So the Blender is not going to be what we thought, because sometimes the application is going beyond the scope that it was designed, but still we will see that what is behind there is the initial idea of the Blender. So what is chaos? Sorry that they are talking in this term. I could be saying transitivity. But let's think in the weak version about chaos. No, we know that this means that trajectories are going to separate either for the past or the future, or the future, not past or the future, or the future. But let's think about a weaker version of that. Is for us, chaos is going to be that if you have an open set and you start to iterate this open set, the diameter of the open set is going to become large. So maybe some trajectory will separate, someone will not separate, but if you have a little open set, then by iteration, this is going to become large. And later, because we want to relate this to transitivity, we are going to assume that this open set, this tiny open set, maybe you iterate one on the future, the other on the past, eventually they are going to encounter each other. And the importance of robustness, and this I will borrow is a sentence that one time Marcelo Viana wrote it, and I think that is clarify why is robustness so significant. And he said that the mathematical formulation of natural phenomena always involves simplification of the physical law. And therefore, when you do numerical analysis, etc., could be missing really what is behind this natural phenomena that we are trying to address. And so what happened, and after this simplification, that the features which are specific of the model are totally unrelated to the actual phenomena that they want to describe. And therefore, the notion of robustness start to play an important role. No? And he said the real significance may be accord only to those properties that are robust under a small perturbation. Okay, so we have this classical phenomenon that people wanted to understand, which is the phenomena of chaos or trajectory moving apart from another. And then the question it was about how this could happen in a robust way. So the typical model to understand, the typical model, yes, that's going to address the robust chaos, nothing else than the stretching. And what is stretching is just take an open set, iterate it, and this open set is not only the diameter that became large, it's going to be the internal radius became large. So in all directions, all the vectors expanded. And you have in the circle, in the torus, a phenomenon like this, that you have this stretching phenomenon. In particular, you are going to see that trajectories separate, and any open set is going to intersect each other when you iterate forwardly and backwardly. Of course, when you do that, your dynamic cannot be a diffeomorphism. It has to be an endomorphism, because you have another open set, and this keeps stretching until you cover everything, another open set doing the same, then you have points that that forward iter are going to finish in the same place. So the dynamic cannot be invertible. And so how to get this robust chaos when you want something to be invertible? The idea is that you are going to have the same, you are going to play the same game, where the stretching is happening in certain directions for the future, and the stretches also happen in certain direction for the past. And the direction where this is happening forwardly and backwardly are going to be complementary. No? So this is a simple picture. So you have U, maybe, I don't know if you can see the hand over here. So they have a little open set. This is going to become this large open set. This is B backwardly, so the direction are complementary. This is envision this in dimension 3. So this open set U forwardly became enlarged on the plane XY, and the V became enlarged by backward iter on the direction Z. And eventually those two sets keep growing, and then they will intersect each other. And this is what we know about the classical theory of hyperbolicity. But let's think about what happened geometrically without defining what is mean hyperbolicity. Stretching for future and past in complementary direction. Okay, but so we have this model, and people have, so this is the landmark of hyperbolic theory. And they say, but this is the only way that this robust chaos could happen. This is the only way that maybe you have this phenomenon of transitivity is only going to happen because you have complementary stretching for future and past. And the answer is, well, we have to wonder about if we can have maybe stretching for past and future, but not in enough direction. This means that it's not happening in all directions. So, which is the cartoon, is this other picture over here. So the open CU is going to stretch vertically for forward. B is going to stretch horizontally, we're in dimension 3. But when you keep doing this game, at the end, this tiny, long, almost, how do you say, wires, they keep missing each other. So therefore, dynamics is not going to be transitive. This is typically what people call this is what happened for partially hyperbolic systems. So you have certain places that you have hyperbolicity, but you have an extra direction where you don't see the stretching, neither for future and past. However, and this was the idea introduced by Magnier and by Mike Schub on the example of this robust transitive dynamic that they were in hyperbolic, is that you don't need to have the stretching all the time. You need to find somewhere. So, which is a picture over here is now you stretch vertically, it became long, but eventually maybe intersects an area, little open say U prime, that now is stretching in 2 directions. Now we came this fat guy on this plane, and there is no problem that they're going to intersect the pre-iter of V. Okay, so we have this little open set, became vertical, and then poof, started to explode on all the direction that you have in the situation of hyperbolicity. And this was built by examples. Okay, but then this is when the ideas introduced by Lorenzo and Christian Bonatti, they kind of see this picture. I don't know if it was like this, but that's matter. This is a posterior narrative, that maybe we can do it better. It's possible to do it better. And what you need over here is some partial stretching that's going to carry the open set to certain places. And we are going to recast this on this notion, carrying, catching, and blending. So what is this? First thing, you need a magic box that mix. So you're saying, okay, so which is the magic box that mix? Well, here in this situation, the magic box that mix your dynamic is the dynamic in itself. It will happen everywhere. Some places, so forwardly you stretch, backwardly you stretch, you mix. And this is the mechanism of mixing or blending. But maybe you don't need to happen this everywhere. You need some place that is going to happen. And this is their magic box, the magic box that mix. Then but still they will be thinking about some kind of partial stretching for future and past, that they will going to help them to carry your open set to your magic box, and then the magic box is going to do the catching and therefore mixing. So here on the top, there is the little box. It's kind of that we don't know how it is, that for some magic property, mix and blend. So you have this little open set and it's going to be inside there distributed everywhere. Then the second level appears this idea that you have this partial stretching, something that in certain direction will be stretched forwardly and certain direction stretched backwardly. And there will be enough to go to this box. We'll go to this box. When they arrive to the box, they are missing each other. By the box, do the gain and produce that they're going to blend the dynamics. So they have this picture in mind, and this picture in mind is going to be extremely powerful because they were allowed to produce at the beginning an example of this type of robust transitivity phenomena without appealing to hyperbolicity in many situations that were not envisioned in advance. So the problem is, who is this magic box? So they have to be some mixers. or this magic box, a magic box that mix, that blend, they were already new, and they were the classical horseshoes. As we have here the picture of the classical horseshoe. So the box, whatever the hyperbolic set, so hyperbolic set were typical mixers. They cannot be neither attractor nor repeller because you need to arrive into the box. You have to come in on the future, but also you have to come in into the past. So this immediately is going to tell you that whatever magic box that's going to mix cannot be neither an attractor nor a repeller. And what happens when you have this box? Okay, you finish going inside the box, but actually intersecting this Cantor set, which is the hyperbolic set, then you are going to mix. But the problem that this type of horseshoes or a horseshoe in principle could be a good mixer, but it could be not a good catcher. Not necessarily a good catcher. Now this is a picture, and to see that it cannot be a good catcher, you have to look in dimension 3. But this is a horseshoe. So I don't know if the color are pretty bad, whatever. So you have a box. What is a horseshoe? You have a box that is going to be stretched, certain direction contracting the other, and you bring it back as a horseshoe. But when you are in dimension 3, there are so many places that if you are coming here, maybe I can annotate. Yes. If you are coming in this direction, you are mixing the horseshoe because the horseshoe hyperbolic set is going to be around here. And therefore, yeah, you go to the box, but the box doesn't catch you. Okay, and so this is a problem. But anyhow, they managed to address this problem just twiddling a little bit these classical horseshoes. It's nothing else that this is the blender. So the blender is a very basic idea you put in perspective, and we look at nowadays. It's just a horseshoe that have certain extra property, but it's so rich in consequence. And if you want to think in terms of picture, you can use, let me remove the annotates. Good. Let's go to the picture of the blender, and I borrowed this design from an article that was written by Lorenzo, Christian, Amy, and Sylvain Crovisier. It's called What is a Blender, and it's really nice to read it. And this is the horseshoes, the blender. It's a horseshoe that avoid this problem that I had before. They've been separated, and they have some kind of overlap when you look in along this direction. And now the catching problem is solved. And again, you can look to this picture that were presented before. We were going to revise this. So here you have this cross cut by the plane Z and X. And so the image of your cube is going to intersect the cross cut in this two rectangle. And if you keep iterating this, so now instead of two rectangles, they have 4, and you keep going. And so what happened that this is really the property that allows you to catch, because whenever you have a segment that is coming on vertically on this way, there's no way that you finish avoiding. There's no way. And you can see here, and they draw in this way. So this is going to help to catch everything. So we go to the previous picture. Sorry. Now I have to remove this. So you go to this previous picture. So how the things are going to be used in a way to mix, because we are going to start with an open set. This open set is going to grow. In this case, it's going to grow in this direction. And eventually they're going to cross this box. And this will not be problematic because the stable manifold in this case is given by the plane ZX. And so you are stretching just on the direction while you are going to cross this plane, and then you are catch. And the problem is when you are iterating backwardly, and then you iterate backwardly. And what happened that you iterate backwardly, they are going to grow in the direction Z. And then we are coming here, but you are going to encounter the blender, and then everything is going to be mixed. So there was a blender, no? It's pretty simple. And this is the nice and beautiful stuff from their creation that is easy to explain and so powerful on the type of consequence they were looking for. Good. So this is the blender. And they produced this robust mixing culture, and the robustness coming from the refinement of hyperbolicity. So if we revisit the sentence by Archimedes, you can say that give me a blender and some partially hyperbolicity. This partially hyperbolicity is about this complementary stretching behavior. Sorry, this stretching for future and past, but without enough direction. And they can say I shall provide robust chaos. So they have a tool and they provide this. And so the situation is much better. Then they can move stuff. The drawing was done by David Sher. That is a friend that is an artist I have. I love this picture because you have the seesaw, which is nothing else than the basic idea of the lever. But it's kind of, the cat going, it's sitting on the seesaw, it's nothing else than the sense of being lonely. But okay, but now the seesaw start to move and produce a lot of stuff. Okay, let's go beyond. Okay, but before that, it's okay. So the sentence is, give me a blender and some partial hyperbolicity and I shall provide robust chaos. Well, maybe it's something that happened in the corner of dynamical systems. But they hadn't shown that actually those blenders and the role that they are playing in producing robust chaos is really more significant than the initial example that they were brought by Lorenzo and Christian. And this is how powerful is their object of their creation and how significant it became in dynamical system. So first, Lorenzo already have observed the blender, even though it's the hyperbolic set, are easy to be found when you are unfolding certain type of bifurcations. And later, using perturbative arguments, and this is happened only in low topology, in the C1 topology, it's possible to prove that those blenders are very common in the non-hyperbolic setting. This hyperbolic setting, remember, this complementary stretching past and future. And when you don't have that, sometimes it's possible to have this blender. So those blenders are already there, they're present. And in fact, a recent theorem by Arthur Avila, Sylvain Clovissier, and Amy Wilkinson that says the following, in the middle of the proof, you can see how a blender are so powerful. So what they prove is that for volume preserving dynamics, either for almost every point, one have zero Lyapunov exponent, or the dynamic is mixing, actually it's ergodic, or transit if you want. Moreover, the dynamics are either hyperbolic, or they have some kind of weak hyperbolicity that allow to do this kind of carrying and connecting to blenders. And in fact, the proof of proving that either almost every point have zero Lyapunov exponent or you have this type of ergodicity, some key part of the proof, there are so many key parts, one of the key is building blenders, finding blender and using them in a way to mix the dynamics. This is pretty nice. Show also how powerful it became in the blender. How people start to embrace the blender and start to use it. The last part is about what happened beyond the blender. So how people inspired by the initial idea of Lorenzo and Christian, and sometimes they were done by them, they start to extend the notion of the blender. And sometimes extend the notion of the blender means what is abstracting what is a blender, and even start to use the blender in places that is kind of the opposite of hyperbolic dynamic or some weak form of hyperbolicity. So let's start to list some results of how blenders have appeared in a posteriori. No? So people have used these ergodic blenders. We will talk later about this. People have started to realize what is the relation between blenders and iterated function system, in particular, the role that they can play in group actions, especially in free groups actions. Recently, in fact, there is some result by Meisana Siri and his student that they were analyzing that in any manifold you can have a group action that they are ergodic, and this is go through the creation of quasi-conformal blenders. Also, a new type of blender which are non-uniform blenders, which is kind of strange because blender in itself is well, there is a hyperbolic set, and this is kind of non-uniform, but doesn't matter. They are going to have the same type of property. This is what I'm trying to say. It's a magic box that catch and mix, and maybe you have to. The idea is that okay, you don't need a hyperbolicity to have those properties, and this is when the objects start to get some maturity. Also, the blender has been obtaining for polynomial automorphisms. Polynomial automorphisms in Z by Z. This is interesting because many of those elements were how blenders have appeared before in literature. It was used it was built or created or formed using perturbative techniques, even sometimes infinitely. But polynomial automorphisms are extremely more rigid. You have to work with polynomials certain degrees. But even surprisingly, in certain classes, polynomial automorphisms in C by Z, they're going to show blenders. And they have so many consequences, their existence. Also, blenders have been obtaining symplectic and Hamiltonian dynamics. We will go back there. Or blendering with something that's not at all hyperbolic, which is the KM. Kolmogorov and Morse, we will explain a little bit more about that. Moreover, recently, finding what is called parablenders. And the funny thing that the parablender will be used to find phenomena that are exactly on the other side of hyperbolicity, even weak hyperbolicity. So we have this kind of hyperbolicity, then we're talking about partially hyperbolicity, dominated splitting, non-uniform hyperbolic. There are some places, there are all concepts where transpires certain notion of weak hyperbolicity. But this is a universe, that is the universe of KM, or abundance of elliptic points, or the Newhouse phenomena that you have coexist on infinitely many periodic points, which are totally unrelated to hyperbolic in principle. But blenders are going to play a fundamental role over there. So I have 5 minutes and I will summarize what is behind those work that I think, and the only reason I want to say that is because I really think that this highlight how important this tool that Lorenzo and Christian have introduced is becoming, how important, how do you say that? It's like how relevant this tool, because it's not just the tool how they saw it, because they have this flexibility, malleability that allows to envision different perspectives. Okay. What were ergodic blenders? Well, the idea is that instead of looking for robust transitivity, people look for robust ergodicity. These are works by Ali, Federico, Hannah, and Raul Ures that show how useful could be also blenders in a certain way to produce robust ergodicity, obviously in the non-hyperbolic setting. Iterated function system, this is something that already was observed by Lorenzo. And maybe this helped a little bit for the student to explain what is a blender. how they affine blender, because I'm saying about blenders that they look linear maps and affine transformations. Can be recast as iterated function system. What is the idea? Well, the picture is really small, so this is the blender. So here, maybe I can show. Here, this is just what is a blender. So what is a horseshoes? No, so you have the button that is being contracted on the horizontal, and so in the X and Y direction, expanding on the Z, and this is the image. Okay, now you forget about the Y direction that is very contracted, and then you have an endomorphism. But it's basically horseshoes where the image of the both rectangles overlap. No? Before this horizontal rectangle, they became here, and now they overlap. And say, okay, but then you have this vertical and stable foliation, and you forget about that or your project. So what you have is an iterated function system. You have an interval that is contracted, but what happened on the bottom, and it's contracted what happened on the top, and displaced. And now you have the freedom to be iterating one function or the other, or the other. Okay. But basically, it's an iterated function system is contracted. And people start to wonder, and this is a work by Barrientos and Rebecca. So what happened that your both dynamics are not contracted? So a certain part that is contracted and certain part that is expanding. No? So you have here you have two maps, F0 and F1 both contracting. This is now you have those two. Can you have a situation like the blender? And what will be the situation at the blender? It will be that your maximal invariance or limit set is the whole interval. Can you have the same here that your limit set is going to be the whole interval? I say, okay, the overlapping is enough, but be careful because you have the repelling point part, you can produce a sink, a repeller, and it could be isolated on your system. And I think that is a pretty nice work by Rebecca's and Pablo Barrientos, that they show that is the derivative of both map are in distance with respect to the identity smaller than 1 square root of 2, you always will find something that the maximum invariance is going to be an interval. And it's not a blender. They have to use some kind of non-uniform blender. Sometimes they are places where span contract, but it's not one that's going to dominate. To do that, they have to really work hard on trying to understand distortion arguments. Good. This idea also helped a lot later to talk about what happened in symplectic dynamics. In symplectic dynamics, you have to tweak a little bit the construction of the blender, because blender here, in the way that traditional were built, they have uneven dimension between the stable and stable direction. Hyperbolic said that an even dimension, and you cannot do that in symplectic dynamics. Anyhow, people had found it, and they managed to use it in Hamiltonian dynamics, in particular to Arnold diffusion. Another example that blender is getting this moving away from hyperbolicity is again mixing blender with Km. Km, what is Km? Well, Km is nothing else that you have a circle, or you want a cylinder, and the dynamic in the cell, this cylinder is foliated by invariant circles that they are rotated with different velocities. So here you cannot have hyperbolicity. Dynamic that they are derivatives is this. So forget about having hyperbolicity. And this phenomena, in certain way, is robust when you perturb. If you have some kind of toroid, the rotation in this toroid, you find that there's no way that you're going to destroy it. So there's no way that you are going to find something that is hyperbolic nearby those guys. However, so if those Diophantine toroid are normally hyperbolic, and normally hyperbolic means that they have complementary direction, that they're contracting and expanding, and they connect in a certain way in a horseshoe, now you produce in this cylinder that is normally hyperbolic and this connection, at least you have to have dimension 4. Remember, in symplectic dynamics, everything can on pairs. A really large transitive set. So we are going to produce in this region large transitive sets. So they are going to play the same role of blender that is related to using this stretching in and contracting not in complementary direction. These are one dimensional. It's two, but using these torides or this circle that is going to be rotated with rational rotation is going to be a persistent phenomena in the symplectic context. Okay, so there is just a little bit of example of something that they have the same property of the blender, play the same role of the blender, and actually was inspired by the classical blender, but wouldn't qualify to be a blender in the strict sense. So this is what I was calling moving away from blenders, but still being a blender. They still have the same properties, even if it's not. Okay, good. And the last part, let me just close with this, is about parametric blender. What is just a parametric blender? Well, it's a hyperbolic set. Sorry. It's going to be a hyperbolic. So you have a hyperbolic set, lambda t is invariant. T is a parameter. And it's a hyperbolic set. Not any hyperbolic set, a blender. And so, because it's a hyperbolic set, it has a continuation. So this hyperbolic set is a blender that has a continuation. It's nothing else. This is it's a parametric blender, but not any one. And they have an important role on finding non-hyperbolic phenomena. Now, what is a classical phenomena that we have? It's about unfolding tangencies. And this is a simple one. So you have a tangency over here, and we know many people know a little bit about tangencies. So they have the unstable manifold, the stable manifold is tangent, and they are going to move. So they're going to be unfolded by the parameter moving up. Classically or typically, this unfolding, the velocity of the unfolding is linear. So Ct is the height that you put here. So it's moving on this velocity. But you can have a non-transversal unfolding, what is called parabolic unfolding, where the unfolding is going really slow. It's like in time it's going to be something like that. Really slow. And what is the consequence of this phenomena? That when you unfold a tangent, you produce a sink. But if the tangency is parabolic, the sink that is created is going to have a long life. So we know that unfolding tangencies produce the New House phenomenon of infinitely many sinks. And if for some reason, okay, so how you do produce these infinitely many things? You can do it, sorry. I go in fast.
Enrique.
Yeah.
Sorry, please take care about the time.
Eh?
A warning about the time, Enrique.
Say it again?
Warning about the time.
Okay, so, okay, time is going to end.
It's ended.
So you have the, okay, so you have this hyperbolic set, and then you produce this tangency, and this is going to produce the phenomena that you have robust tangency, and robust tangency giving you the coexistence of infinitely many things. But if for some reason you have this parabolic unfolding, is going to be robust, that would you produce that is coexistence of many things holds for all parameters. So you have to find a way to produce the robust parabolic unfolding. And this was the, I think, a wonderful contribution by Pierre Berger, that he said, okay, but how do you find this robust parabolic unfolding? And he realized that it can be done by certain way that you move blenders. And this is what they call parablenders. So parablenders are nothing else than hyperbolic set that the majority of their points they move parabolically. And this was kind of amazing because blender was kind of very hyperbolic set, very useful for robust transitivity. And now when he embed in parameter, he realized that they're going to have an important role of bringing us a new phenomena that we didn't envision yet. We didn't envision like 6 years before. And it was very, I think, very powerful. In a later work with Sylvain Concrisien and myself, we realized that actually those parablenders, so the blenders, they have this kind of parabolic, produce those parabolic behaviors. When you look at those parablenders acting on a space of sheds, what is shed? Well, because you are talking about curves, which is the movement of a point, how they act over there, they are actually blenders in an extremely higher dimension. But anyhow, those parablenders that became so powerful are actually blenders when you look in higher dimension, in the space of sheds. Anyhow, so I hope that I could transpire this idea that an object that was introduced 26 years ago, maybe more, and that it was very clever and well how to design it, is gaining this maturity in terms of the influence that is producing, not only because they are finding the initial object everywhere, because also encourage people to imagine, I don't want this, new ideas. Okay, so that's it, I think. Let me finish with the last.
Thank you.
The typical that you put a picture of the guy that we want to celebrate.
Okay, thank you, Enrique. So as Archimedes said, give Enrique 35 minutes that he finds much more minutes and carries you to many, many rich mathematics. Thank you, Enrique.
I don't know if it's a compliment or it's just a satiric comment.
No, this is just a thank you. Thank you. So
it's a satiric compliment, very positive, but with some satire, but very positive comment.
I'm just worried about Christian's night. I don't know if Christian permits us. We will have still some 3 minutes maybe to begin. If somebody wants to say something about these wonderful blenders, parablenders, etc. So, is there any comment? Just I would like to say, as I understand, you said that okay, this is a mechanism, and it is not a hyperbolicity mechanism. It came in the realm of hyperbolicity, but it is some kind of topological. So, in the essence, you have some kind of covering, this covering properties or overlapping. Something else is happening. So it's sometimes hyperbolicity enters, sometimes non-hyperbolicity enters, etc. So this is kind of magic tool that you introduced. Do you agree or?
Whatever. I think that what they have done, this was surprising. But the role, the first is simple, and we like simple things. Exactly. And we love something that is very simple and they have so many powerful implications. But we love also that it's so flexible as a concept that it gives us the opportunity to try to see this object in the different context that it sometimes goes beyond the way that the implication of the object, beyond the idea that I have in mind at the beginning.
Mhm.
And this has been absorbed not by just Christian and Lorenzo, by the community. So this is the maturity of an object. So it has been embraced by the community and using this object in different perspectives and identifying the principle on what they did, on what they keep doing. And I think that is wonderful, no? So
Okay, thank you.